Welcome everyone. GOBC Chem 114 lipids. We've been talking about two different types of lipids, including fatty acids and the steroid nucleus that makes up these very interesting molecules that are kind of larger than anything we've looked at thus far. So we talk about waxes. Waxes, they're a combination of fatty acids and lipids. They're used as protection, a source of waterproofing, things like that. We also use waxes as humans for our shoes, our floors, all sorts of cool things, our cars. Um, Here's some bees. There is honey, but of course, there's also beeswax. So bees are very important, aren't they? Anyhow, waxes, quickly, you've kind of seen this already, but it's really the same thing as an ester, but the chains are a little bit longer. They tend to be longer than just with fatty acids. They tend to be saturated and longer, up to 30 carbons or so. Again, they're a source of waterproofing. They can protect plants from losing water to the hot sun, right? So the plants don't dry out by using a wax. So you can see the fatty acid, the carboxylic acid that can react with a long chain alcohol, which forms an ester. So this is an ester, not a carboxylic acid, but it came from a carboxylic acid and an alcohol. So some examples you can see already if you think about the fatty acids we looked at last time. Look at the difference here. These are much, much longer, aren't they? 29 carbons. We haven't seen anything like that yet. And everything is saturated. There is no very little unsaturation in these waxes. You have beeswax, comes from honeycomb. You have carnauba wax, which comes from Brazilian palm trees. You have jojoba wax, which comes from a bush. And these things are used in different industries. For example, beeswax can be used in candles and shoe polish and wax paper. The carnauba wax can be used for furniture, for floors, for cars, for shoes. And the jojoba uh, wax, again, candles and soaps and cosmetics. So, you know, awesome. So we're learning just from carboxylic acids forming esters, these long chain fatty acids that react with a alcohol. And in this case, a huge alcohol would have been used if this was made synthetically of over 29 carbons long. You haven't seen anything that big yet. So it's very water insoluble, right? Very much so water insoluble, right? It dissolves in oil, it's insoluble in water. And if you would mix them together, you would get two different layers. Hopefully, in lab, maybe you've had a chance to explore using a funnel or done organic chemical separations. Um, well, moving right along, we've already learned a little bit about triacylglycerols, about and we'll take a look again. Remember, the glycerol molecule is has three alcohols on it. When we take a glycerol and react it with three fatty acids, we get triglycerides, which is a whole class of molecules we talk about in humans and animals and other places. But anyhow, we know that glycerol being an alcohol, a trihydroxy alcohol, and you can react that with fatty acids with the carboxylic acid, and you get esters of that glycerol, which make up the triglycerides. You have three hydroxyl groups on that glycerol, which is a trihydroxy alcohol. It's an alcohol just like ethanol or propanol, same kind of properties. Um, and it can react with three fatty acids with three hydroxyl groups. But when this happens, the name of glycerol will become glyceryl. Okay, so I'm not going to make you be able to name these molecules readily. That's just a little bit much. We really need to know the structures, and some naming things can be helpful at this stage. Taking a look at glycerol, the trihydroxy alcohol, it reacts with 3 fatty acids. In this case, it happens to be a saturated 18 carbon stearic acid, and it reacts with 3 of those in one reaction process. And then we get this glycerol, which is referencing the glycerol part, glyceryl from glycerol. And then we get this tristearate. It went from stearic to 8 because it kind of becomes a little bit like a carboxylate in how we reference it, as opposed to a carboxylic acid as it's seen, stearic to stearate. Okay, and with there's some common name that's used in the industry. Maybe somebody needs to order this up for some kind of project, and it's glyceryl tristearate or tristearin, right? And it is a dehydration reaction. You lose water. That is what they're showing in this green box, the loss of water in the reaction process. Okay, the human body can do this, but we can do this in a lab too, right? So what happens here if we mix different fatty acids? And enzymes can sometimes do that. They can put a certain fatty acid at the 1 carbon, or they can put a certain fatty acid at the 2 carbon. It can be saturated or it can be unsaturated. And at the 3rd carbon, it may put a even different fatty acid. So think about the specificity of that. You mean the body's so complicated it can make these real unique molecules? It's fascinating, right? Stearic acid goes to 1, the oleic acid may go to carbon 2, and then palmitic acid to carbon 3. How do we get such specificity? This would take us humans days to figure out, or years. We may have things we may be able to look this up and find out how this could be done, but we could use blocking groups, and I'm not going to get into that. If you go further on in your career and you love organic chemistry and you like the idea of making all these cool molecules, there should be a place for you in this world. But just remember, we look at the stearic acid and palmitic acid. What do they have in common? Well, they're saturated. There's no double bonds in it. But we look at oleic acid. It does have a double bond, so it does have a point of unsaturation. So oleic acid is going to be considered a unsaturated addition to this alcohol group. And how many carbons? That's one of the easiest ways to classify a fatty acid, is by how many carbons. 1, 8, 9, 10, another 7, 17, 18. So oleic acid is always going to be 18 carbons long, and stearic acid is going to be 18 carbons long, but it doesn't have any. It's like oleic acid. It has the same number of carbons, but stearic acid has no point of unsaturation. Okay, and palmitic acid has 16 carbons. So that can be helpful in identifying these. Triglycerols are a source of energy storage. Okay, so we know the short-term energy storage molecule favored in us is glucose, but we can also store glucose as glycogen. And that's kind of short-term blood sugar level type mentality that we need it now, we need it today. But triacylglycerols can be stored in fat molecules and can actually be another source, a secondary source of energy. And animals, in fact, when they hibernate, they eat a lot of plants and seeds and nuts that are high in these calories of triacylglycerols. They can store them in their body in a particular way so that when the temperature, of course, drops, the animal goes into hibernation, and the body temperature, of course, drops, as well as the metabolic speed, the metabolic activity goes very low. These molecules can also help the body from freezing because they're resistant to freezing in water. If you put these molecules in water, it will lower the freezing point. So the freezing point becomes, instead of 0 degrees Celsius, maybe it becomes minus 30 degrees, right? So lots of uses for these molecules in humans and in industry and animals. And so this is a way the animal can store some energy through these triacylglycerols. And there's a way for fatty acids to be broken down in the mitochondria and other things that can happen. And another, what are the fatty acids in the following triglycerol? Typically, you look at what? How many carbons do you have? And then how many points of unsaturation are there, right? So this is 16, 17, 18, right? And then this one here, is 1, 8, 9, 10, 17, 18 as well, remember? And then here we got 14. So we want to identify the fatty acids. We know what? We know that this molecule is going to be came from glycerol. Of course, that's in the human body. It's also can be used for other things in industry. It could be used for antifreezes and stuff. And here we see stearic acid, oleic acid, and myristic acid, which is 14 carbons. Palmitic acid was 16 carbons, right? So memorizing these can be important in certain classes in biochemistry. Here, metacognition, how would you go about solving this, right? This molecule being called tripalmityl-oleic acid. What is this exactly here? So you see that if you see tripalmitic, you probably know, oleate, you probably realize it may be a combination of one or two um, acids. In this case, it's going to be three palmitoleic acid molecules. So there's not three different types of fatty acid in this case. There's just one type of fatty acid repeated 3 times that will go with glycerol, unlike what we last seen. And so if we were to draw this out, we would need to know what palmoleic acid looks like, palmitoleic acid. It's 8 when it is bound in the molecule of alcohol. It would be ic, it would be tripalmolate acid. You'd have IC here. It'd be oleic. So palmitoleic acid, but it becomes palmitoleate as the carboxylate. Remember, when you remove a proton from a carboxylic acid, you get a carboxylate. In general, take a carboxylic acid, it gives up its proton, it becomes a negatively charged species, right? Remember, we went over that a few times. Review what a carboxylate looks like. And also, carboxylates have the resonance that I drawed and displayed. A little bit important here, but moving on, all of the all of the fatty acids attached to the glycerol are all the same. There's no difference. So it's tripalmitoleic acid that was it's glycerol. And I'm not the greatest at naming these because that's a lot of time. But do know a little bit about what you're seeing if you see the name. If you're in medicine, you kind of know what this means, or you're in pharmacy or industry. Draw a condensed structural formula for a triacylglycerol containing 3 molecules of myristic acid. And by the way, they give us that there's 14, meaning 14 carbons. They put a 0 here, and that means there's no double bonds in it, so it's a saturated fatty acid, and there will be 3 of them. And we know what glycerol looks like. So the acyl, well, what do they mean by the acyl group? That's this right here, right? So if we were to try to, the acyl group is right here. This is the acyl group, right? The acyl group, acetylation. Excuse me. No, let's take away the oxygen. For the acyl group, we would be talking about this, right? For the acyl group, we would be talking about this. Okay. And there's different ways to look at these molecules, right? We've talked about how the alcohol reacts with a carboxylic acid, it makes an ester, but we can also call that carbonyl and the other long part of the chain an acyl group, and a long acyl group. It could be a generic name, or it can be just a C double bond CH3. For example, a lot of times an acyl group is simply this right here, CH3. Right? So that's acetylation often means that, but they can use this a little bit differently, as you see they do here in calling this triacylglycerol. Um, and that's good. Let's move on. That's the fatty acid that the 3 fatty acids that combine with glycerol to make this molecule, this lipid, this fat. Okay, so melting points of fats and oil. If you can imagine, a fat is typically, if we're defining it at room temperature or how humans see it, it's a solid at room temperature. So its melting point is higher than room temperature. But for an oil, it's going to be a liquid at room temperature. And what does that mean? If it's a liquid at room temperature, it probably had a much lower melting point, meaning it's easier, less energy is required to melt an oil as opposed to a fat. And we learned that fat molecules stack very well and tightly and have more stronger intermolecular bonds between themselves. So it takes more energy to melt fat as opposed to something that's already oil. Fats can be found in animal sources, meats, milks, butters, and cheese. Milk can be a fantastic way to get your fats, even proteins and sugars and all sorts of stuff. Of course, there's people that are lactose intolerant, and then milk can be a problem. So oil, a liquid at room temperature, it could be obtained lots of times from plants and palm oils and such. And so that's kind of a generalized difference between the two. Do remember, using chemistry in the lab, we can change different things, right? We can hydrogenate something, and unsaturated bonds can become saturated and therefore turn an oil into a solid in some cases, right? But thinking about oils in general, they can come from olive and peanut. Peanut oils, and they tend to be monounsaturated. They only have 1 degree of unsaturation, one double bond, and that's it. But that still is enough to make them flow more easy than a saturated. So you should know unsaturated and saturated. That should be second nature as you memorize things. Corn, cottonseed, safflower seeds, sunflower seeds are polyunsaturated. They contain multiple double bonds, multiple points of unsaturation. You can, of course, hydrogenate them with H2 gas and platinum in a lab, and then you can get rid of those double bonds and turn them into single bonds. But when you do that, you may lose the oil-like flexibility. Next up on the list is palm and coconut oils. Often they're solids, and because they're mostly saturated fats, and we're going to find out it's a little bit more, these extracts of plants are sometimes not just unsaturated unsaturated and saturated. We'll look at a chart here in a second that'll give us an idea which has the most unsaturation of its extract and which has the more saturated, right, within the plant. Now let's look at a molecule. Again, this is 18 carbon. It's unsaturated. You can think back to what was 18 carbons, and I think was it oleic acid. Um, and so this is trioleate, right? Because oleic acid, once it loses its proton, goes from oleic acid to olate. Okay, that's a carboxylic acid. When it loses its proton, it goes from oleic to olate. The EIC changes to ATE, right, as you see here. Boring, maybe not, but you're learning. You're getting introduced to these things. You may have wonderful ideas. Some of you might be entrepreneurs, even in the medical field, to come up with wonderful things to help all of us humans, right? So these, again, no surprise. If we have a kink like that from a double cis, that is a cis bond. It's an alkene with a cis bond, and it kinks it. It's not, if it's a trans, it wouldn't be that much of an effect, but it is a cis bond introduced, and it causes a kink, and it can't stack and pack together quite as well. So guess what? It's more flexible than, say, um, a saturated fatty acid. This is an unsaturated fatty acid, right? This is unsaturated. And then for some reason on the slide, they talk about saturated. Well, saturated, if we were to turn this into a saturated molecule, we have to get rid of these double bonds and put hydrogens here. We'd have to use hydrogenation. We add two hydrogen bonds, two hydrogen bonds across the double bond, and we turn it into a single bond with the addition of a hydrogen at each carbon, right? So that would make it saturated, and that would effectively um, uh, increase the melting point. You would have a higher melting point when you get rid of degrees of unsaturation because they could pack together tightly. And animals and coconuts and animals, fat, coconuts, palm oils all have more saturated fats than not. What do I mean by that? Let's look at our wonderful table. So, percent of saturated and unsaturated fatty acids in fats and oils. So, you have to take time to look at what this is saying in front of you. What does the table say? What is the thing nowadays? Our attention is so drawn into so many places, we miss detailed facts because our attention span is pulled in the direction of all sorts of things. What's on my phone? What's on my web page? What's on my social media site? Not the student's fault, but it does make it difficult to focus on the details because you're going 90 miles an hour in 10 different directions. I don't even blame the student. But you want to take a look. What does this really say? It says polyunsaturated, monounsaturated, and saturated. So we know that color bar is responsible for the percent of that material in a selected fat or oil. So if we were to look at corn, and we'll just look at a couple of them, corn tends to have a lot of over 50% monosaturated fat. So it's kind of like an oil, right? And it does have a little bit of saturated fat at about 15%, but it also has a lot of unsaturated fats at 35%. So this bad boy is an oil. And we look at olive oil, it has a whole bunch of monounsaturated. So it does have at least a lot of molecules of only one double bond, but that's enough to make it an oil. And it has some saturated. So it does have about 10% saturated materials, which usually is a hard, solid fat. And then it has some polyunsaturated, which is going to make it very oil-like. So we can assume the solid oil fats or oils are going to be mainly what? They're going to be predominantly saturated fats without any double bonds. Coconut, certainly, over 90 some percent is saturated molecules of fatty acids with glycerol. Butter, again, over 70 some percent of the molecules in butter are going to be saturated. And beef tallow, it's not far behind. It's almost 50% with the unsaturated fats, giving it a little bit of, it's still a solid fat, but it's not quite as solid as some other ones. And then we have polyunsaturated fats, hardly any. Coconut has no polyunsaturated fats. So how healthy is that? I don't know. I'm not a doctor of fatty acids. So that ends it. That ends it. You guys have been awesome. I will see you again in the next section, and 15.4 we'll go over that and some more great stuff about unsaturated, saturated molecules, and we'll go even deeper.